Okay, so welcome back. Uh, yeah. So the speaker for this afternoon is Professor Dingping Tsai, Tsai Dingping. He's a physicist known for his work in the fields of photonics. He's currently a distinguished professor at the National Taiwan University and director of the Research Center of Applied Sciences, Academia Sinica. He has been president of Taiwan Information Storage Association since 2015. Professor Tsai obtained his PhD in physics from the University of Cincinnati and subsequently worked as a researcher in California and Toronto. He became an associate professor at National Taiwan University in 1999 and was director general of the Instrument Technology Research Center in Hsinchu. Okay, so let's welcome the speaker. The stage is yours.
Okay. Good afternoon. Thank you for the host. Thank you. Yeah, thank you for the introduction, and also thank you for the recognition of this award. I really appreciate this great opportunity to present our award paper. And the title of my talk is New Vision of Metaphotonics. However, the awarding paper is a broadband achromatic meta-lens invisible. I am currently in City University of Hong Kong. I moved to Hong Kong in 2019. Okay, so this paper actually was a collaboration research work with Nanjing University and also Taiwan University and Academic Sinica in Taipei. Yeah, this is a very interesting work. So I simply use 30 minutes to give you a very short introduction of the story. Basically, we know the metamaterial is a new material which based on the new principle. The principle is quite simple. We know all the natural material is forming by the atom and the molecule. However, people try to make the artificial atom or molecule. And this definition of metamaterial is the artificial atom and the molecule has to be less than the wavelength. In this way, the size of the meta-atom and the meta-molecule basically is smaller than the wavelength. So it will be considered as uniform for the wavelength, working wavelength. So it's not discrete structure, but a uniform material for the working wavelength. That's the basic principle and the definition of metamaterial. Okay, so with this in mind, basically you can consider for the interaction of the light, actually for the plane wave coming to a very flat surface, geometric flat. Basically, your light comes in and goes into the material is similar planary wave. If you tilt a certain angle, it will actually follow the Snell's law, which is determined by the index of refraction difference between the incident medium and the second medium. Okay. However, if you have some feature or structure at the interface, then you have to consider the reconstruction of the wave. So that's why the generalized Snell's law, you have to add up the contribution from the interface of this surface. Okay, so this is so-called the meta surface. Meta surface, actually, the surface is formed by the artificial structure, man-made structure. It's a narrow scaled structure, smaller than the wavelength. So in 2011, people use this man-made artificial structure, the V-shaped structure, which is gold here. Actually, they are able to have this incident wave reconstruction, forming the secondary wave, and this wave have the contribution given by the artificial surface. They demonstrate this kind of different narrow antenna forming the different phase, and this phase contribution will control the light of the incident light and reflection light. So for the electromagnetic wave, basically you can control a lot of parameters using this way. So, and then you ask the next, what's the next? If you can control the diffracted or refracted light, basically you can form in the mirror or lens of this structure. And this is the reason for us to consider to make the meta lens instead of traditional lens, because traditional lens, if you want to make very good lens, you need to have a lot of lens together forming the lens set. It's very bulky and expensive. However, if you can make this kind of meta lens using the artificial narrow antenna to diffract the light, to focus the light, then you are able to do a lot of application, use this kind of lens. So with this in mind, people first demonstrate for different color showing its narrow antenna in one dimension, which corresponding to the diffraction of this wavelength, because every narrow antenna actually they resonance at one frequency. Okay, so in this way, to have a lot of light focused together to get rid of the chromatic dispersion, you have to make this a set of antenna in one dimension and showing this focusing at the same spot. This is the way to make a useful lens for imaging, because for imaging you have to see everything, all different frequency or color, and showing the real image like your eyes. So people first use this kind of demonstration. They also use the RGB, red, blue, and the green 3 lens to focus at the same spot. But all this kind of demonstration are discrete, means you design the narrow antenna, but they focus at the same spot, but they are not continuous broadband. They are discrete for certain wavelengths. So it becomes a challenge for people to have a broadband, continuous, all the wavelengths focus at the same spot. That's the basic requirement for imaging of everything. So this challenge happened in the 2017 and the 2016. So then the people ask this question, can we do it? Basically, if you check, you have a matrix, and you basically consider your meta devices. It's like a transformation matrix. And then you have input. You know your input, you know your output. Okay? The output is your requirement. You basically can calculate and find out what kind of matrix tensor you should be. You should be able to have it. Okay? So this transformation matrix, in principle, you can do it. However, in reality, it's very difficult. The reason is you have to be like the God. You play the meta atom, and you put in the different X, Y, Z location in order to fulfill all the requirements. And also, people have some demanding for application. For example, they need to have a certain wavelength and polarization and amplitude and all sorts of requirement. So in this way, you have to balance all the parameters and optimize for the reality, because you are not the God. You have limited meta atom to put on the surface, and you need to make each of them. So how to do it? And this is the background and beginning of the story. How to do it? Then we have to go back to think about all the material. Even the metamaterial has the advantage is the artificial atom or molecule can provide you with novel function which is not provided by the nature material. That's why we make so much effort to make the metamaterial. Otherwise, you simply just use nature material. Okay, so with this advantage, then you have to consider the material you used. Still, they have the permittivity and the permeability, and they have index of refraction, and they have extinction coefficient, which is wavelength dependent, and also which is related to the geometric and configuration of the narrow antenna, or narrow or meta atom or meta molecule you made. So you have to first to think about it, what kind of material. For example, you choose the gold, it's a metal, or you choose the gallium nitride, it's a dielectric material, or you choose the silicon, it's also a dielectric material in certain wavelengths and become the metallic in certain wavelengths. Okay, so all kinds of material plays a different role. Then you have to do some simulation and calculation. Either use the program you made by yourself, or you can use the commercial software, but with limited function. And then you have to figure out the efficiency and from the transmission and the reflection curve spectrum, you can find out the efficiency, phase, polarization, and spatial wavelengths they can resonance. Okay, I will talk about this later. Then you also have to understand how to make different function which is demanding, and you have to also know about all this meta surface layout on the surface, how to make it most high efficiency with very compact and very good arrangement. And finally, you have to know about how to make those narrow antenna use the semiconductor microelectronics process, or you use some new technology like narrow imprinting, or like different way, 3D printing, those way to make your sample. And then you have to characterize whether it's working or not. Basically, you can collect the big data. You can use the AI to help you to do all this design and all this arrangement. So in the beginning of this kind of system, people think about all this narrow antenna, how to control the narrow antenna to make a different phase contribution from 0 to 2 pi. Okay, so if you have only one narrow antenna, actually the oscillation is from 0 to pi, not 2 pi. Okay, so how to make it? That's why at the beginning people use the V shape. V shape means oscillation from this direction and then go to this direction. So to make it 2 pi. Okay. Or they use this metal sandwich dielectric material and metal. So this oscillation like this, the EM wave comes in. The narrow antenna has a plasmonic oscillation, collective electron oscillate. And underneath the mirror has a mirror image. There is a opposite charge on the another mirror side. So they form in this virtual current and generate a magnetic dipole. So in this way, they have the electric dipole oscillation and then pass the energy to the magnetic dipole oscillation in order to form the 2 pi oscillation control of the phase. So all kinds of way the geometric phase control means you have a narrow antenna. You rotate theta angle, then the phase change to theta. Okay, so you use this way. You rotate 180 degrees. Actually, the phase change to pi. Okay, so all kinds of this narrow antenna you can play, and also the propagating mode means that you actually tune this narrow antenna size, the propagating wave inside the narrow antenna. They can be tuned from 0 to 2 pi. Okay, so there are many ways to play this game. However, in our case, we actually in this paper, award paper, we introduced a few novel idea. The first one is we take the focusing equation to take the differential phase equation and to have two parts. One is the basic phase part, another part is the phase compensation part. Okay, I will talk about it later. And then we also introduced the edge alignment method. The traditional lens, basically the lens is curved. In the center, the light goes straight through and bending the light at the edge. But in our case, we actually make the edge has a less phase contribution, but in the center has the highest contribution. So we align the phase as an edge and then has the highest phase difference in the center. Okay, and also we use the geometric phase contribution for the basic phase part, and we use the integrated resonance unit for the phase compensation part, and then we can make the different wavelengths. They have a different curve, and we choose the center one, and then we compensate the lower minimum one, and also we reduce the maximum one. So in this way, we make the whole arrangement of the meta lens in the easiest way and the best performance way. Okay, so then I want to talk about the integrated resonance unit. What is the integrated resonance unit? If you have one antenna, basically this antenna work only for certain wavelengths of frequency. It's not the broadband. You never had the one guy can be the president and also can be the doorkeeper for one company. Okay, so that's the one-man company. Okay, it doesn't work. Okay, so you have to think about it. For example, in the beginning, people had a headache. You have a headache medicine, and then your stomach feel uncomfortable. Then the doctor gives you the stomach medicine. Then you eat the stomach medicine, and then after you eat all of them, you feel you have a fever. Then they give you the fever medicine, and so but in the Chinese medicine, basically they give you a lot of things. It's different thing. They actually check your pulse, and they give you the first day, and second day, and third day. They give you a lot of things and put together and to drink all this medicine. So this is like a whiskey. Okay, you put a lot of things together, and also in the previous case, they don't care you are male or female, you are old guy like me or young guy like you guys. Okay, so they give the same medicine. But in this way, it's the precision medicine. Okay, they actually test your pulse. They try to make the medicine adjustment every day. You take a different medicine. It's a precision one. So that's why we introduced this idea for doing the integrated resonance unit. That means our meta atom, not just one antenna, but a lot of antenna. Okay, so for example, in this case, okay, for example, we have design of this meta lens, 50 micron diameter, and underneath is a gold mirror, and then the silicon dioxide, and then the gold narrow antenna on the top. And in this case, basically, we have, for example, A to the W, they corresponding to the phase compensation from 30 degree to 360 degree, okay? And for example, in A, they have the width of the 40 nanometer. This is width, okay? And length of 450 nanometer, and times 5 means those two times 5, that means they have 10, okay? 10 narrow antenna. And then the gap is here, it's 25 nanometer, okay? And all of them are different, okay? And they corresponding to the different compensation phase, okay? So this is the idea of integrated reference unit for doing the compensation. And we took the advantage of the lens's symmetry. It's a center symmetry, okay? Circular symmetry. So you just need to design 1 pi, okay? Then you put all together. You just need to calculate part of them, and then you can put together all of them. And each part from 0 to 40, we actually design a lot of different elements for all the area, okay? So that's the way to make this kind of thing. However, the previous case is gold underneath, so it's only for refraction focusing, refraction type of metal lens. People ask, they want to have the glasses like my glasses. It's dielectric transparent. So we use the gallium nitride to make this kind of narrow antenna, but it's negative. It's not the positive like antenna and rod, but a cavity, a hole into it. And we rotate it with the geometric phase control for the basic phase. And also we had the compensation of the propagation phase control from 0 to 2 pi. Okay, so this is the way to make this kind of a lens. And also we have SEM picture showing this is the metal lens 50 micron diameter, and the center part here, and the part B showing the narrow hole and the narrow antenna, narrow rod, the edge, and then this is the narrow rod region. This is the tilt angle, which showing the narrow rod. It's 800 nanometer narrow antenna. And this kind of narrow antenna, which is all different at the different location, they are all different. Different in size, different in rotation angle, and different in all the way. But it's circular symmetry. So you can make your design much simply than the other ways to do it. So this is the advantage, okay? And so this is the performance from 400 nanometer to 660 nanometer in the visible spectrum. It's a continuous broadband in the visible frequency, okay? So this is basically the first time for the man-made metal lens which can show the color image. Okay, first time. Okay, previous in the 2012 and the 2016, people show the metal lens, but it only work for single wavelengths. It's not for imaging. It's for only for focusing the light to a one spot. Okay, but it cannot use for imaging. For the first time imaging demonstration, this is the first time. I think that's the value of this awarding paper. Okay, so then we, my student, they like seeing the cartoon. They took the cartoon and they demonstrate efficiency is very high, and for different type of, they make a lot of metal lens, and then they compare each of them. So then I have to talk about it is, I still have about 12 minutes. So I let you just try to remind you, in the beginning, 2006, Professor John Pendry visited me, and then we published a paper. It's dielectric material and made phase change material, and we make this so-called hyperbolic metamaterial. And this kind of metamaterial can have super resolution imaging purpose. So it was published in 2006, and also in the 2012, we have collaboration with Fudan University, and then they had a student to become my postdoc. So we make this gradient narrow antenna. The gradient narrow antenna actually give you the contribution of the meta surface, so they deflect the light. So this is actually the first time demonstrate the light beam can be deflected. Okay, it was cited more than 1,000 times, and this paper give you the idea. Actually, you can focus the light if you control the diffraction. Okay, so that's the beginning of the whole story. And then we make the meta hologram first time, and with different color. Also, it's a full color meta hologram, and RGB, different color and different imaging. And also, we make the tunable. We use the electric tuning, the epsilon near zero of the semiconductor material to tune the index of refraction to make the light beam deflect to scanning different angle. And for this one, we control the polarization, and we also can analyze the polarization. And this is for generate the toroidal metamaterial and toroidal dipole, and also anapole. Anapole is a very interesting thing. You generate the electric dipole, and you also make another toroidal dipole, which is exactly the same direction, but opposite in the propagating or oscillation way. So they cancel each other to forming the anapole. And we also use this full pixel level full color routing. We make the surface like a color filter. We replace the color filter, but you know all your cellular phone has a CCD camera. All the CCD camera currently they have the RGB3 sensor. Okay, they collect the RGB, and in front of the RGB sensor, the backside is only silicon sensor, but in front of the silicon sensor, they have the red and blue and green filter. So the light comes in. For example, 300 photon comes in, and then they only collect 1/3 of the photon to their detector. And for this case, we actually had the light comes in, 300 photon comes in, and all the detector collect all the light, not 1/3, because they waste a lot of, in the current way, the CCD camera, they waste 2/3 of the light. But in this case, all the light comes in, they goes to the right sensor directly without blocking or waste, because all the sensor, they had only, 3 elements. The other 2, they actually waste. Okay, so that's a way to make this, and this also is a very important development. And today's talk actually is talking about this. The first time demonstrates the imaging of the true color and the broadband, continuous broadband imaging. And later, we make this lens, many of them. For example, in this case, we make 60 by 60 lens. So it forming a lens array. The lens array is very important because the lens array, each lens actually are located at a different position. So it's different angle to seeing the things. Okay, so they collect the information. It's not just plenary two-dimensional information. They collect actually different angles of the collect the light field. Light field means they collect three-dimensional matrix information into the imaging system. Okay, so this is a demonstration of the light field. Light field showing they can see many things, not just planary, but the depths. Okay, and this one also very interesting is for doing the meta lens, which narrow antenna can generate. For example, you have one wave, for example, 600 nanometer wavelength comes in. Okay, you can generate the light actually to the 200 nanometer or 300 nanometer, depends on its second harmonic or third harmonic. The narrow antenna, they absorb the light and then they emit the shorter wavelength light, and also they focus the light according to our spatial arrangement. So we actually make the shortest wavelength using the meta lens. How short of this wavelength is 197. 197 nanometer wavelength. The meaning is they had a very high energy. It's so-called vacuum UV light. And you say, what's the vacuum UV light? Okay, we know the infrared. We use the infrared for the night vision. Okay, we don't like the ultraviolet UV light because it hurt your skin. Okay, skin cancer caused by the UV light. UV light is from 200 nanometer to 350 nanometer. Okay, that's called UV light. And below 200 nanometer, it's called the vacuum UV light. The vacuum UV light means that it has to be in the vacuum to detect it. The reason is the photon energy is too high. If there's some air, like the oxygen or hydrogen molecule in the air, this light will collide with this molecule and decompose the oxygen or hydrogen. So you have to be vacuum. This light can propagate. So it's called a vacuum UV light. And then people ask me, can we make this for the photolithography for the semiconductor 5 nanometer or less than 5 nanometer? In principle, it's possible, in principle. But you have to consider how to do it. So this is all very interesting. And also we make this in the biologic application because our lens is very small. In the last 400 years, people make lens. The lens become very cheap. But there's a challenge to make a small lens. That's very difficult. But now we can make very small lens. This lens is so small. This is the, the intestine, the vivid on the intestine of the mouse, 小老鼠肠子里面的绒毛。This picture, okay, so this poor mouse is very sad. Okay, actually passed away already. Okay, but anyway, if you want to make the small lens, it's a challenge. So because of my time, I have to catch flight back because I have to go overseas for another international conference tomorrow. So I have to catch my flight from Beijing to Hong Kong. So I think all of these are very interesting. And I moved to Hong Kong, and I think my university, PolyU and the CTU, their support. So we have a very interesting project. It's called the Meta Optics, Meta Acoustics, and Meta Devices. It's an 8 years project. And we have many good professors join our team, including the Professor Sir Jiang Pendry and Professor Tanaka from Japan and from UK. And we actually had also still recruiting our student, and we have a postdoc and PhD student in the CTU. So you are welcome. I think many excellent young and talented scientists and students are very, very welcome to join us. So I think I stop my talk here. Thank you.
Okay, thanks for the beautiful talk. Is there any questions from the audiences? What's the question from audiences? Okay, sure.
You mentioned the feature has to be much smaller than reflection and one tank. And what's how do you typically select the feature size? Or what's the implication?
Oh, okay. Basically, like I mentioned, depends on the application and the requirement from the application. We have to think about first the material, okay? And different material can form the different narrow antenna, okay? Like a metal or dielectric or semiconductor, and different material has a different process technique, okay, like the focus ion beam, E-beam, and also narrow imprinting or 3D printing, or there are many ways to do it. So in general, basically the narrow antenna has to be follow the control from 0 to 2 pi. So we have to consider how to fulfill the fully control of the narrow antenna first. And then we can make the size smaller and smaller and smaller. Yeah.
Okay, so thanks.
Another quick question. I think you mentioned about the UV focusing. So that's why based on you have to have a certain nonlinearity.
Yes.
And,
yes.
What's typically the efficiency that you achieve?
Oh, for second harmonic and third harmonic efficiency, basically is very low. And also for traditional nonlinear crystal, they had a lot of atoms and molecule in this crystal. But in our case, we only had single layer narrow antenna or narrow atom or narrow molecule. So it's very challenge for us to make it very high efficiency. So typically, we want to make it high, but compared to the traditional one, still quite low. So that's why we also take advantage of the surface. We make the surface area bigger, and the narrow antenna number becomes large, and they all focus at the same spot in order to make it feasible for the application. But still, it's like you say, you are correct. It's not easy. Yeah, we do our best. So right now, the highest record we made is still there. Yeah.
Okay, so are there any other questions? I have one actually. So could you help me understand the basic? Is each small lens, it acts like a separate lens, traditional lens, or you need to actually use all of the small lens so that they can their interaction gives you the effect.
Sorry, can you say it again?
I don't understand. So your each lens is very small. So
yes.
How do you handle the interference or diffraction?
Oh, okay. For the narrow antenna we made, basically it's look through the light. It's much smaller than the wavelengths. They treat them uniform. They don't see the discrete of those atoms. They treat them uniform. But so in our case, there's no those diffraction spot. No diffraction spot. It's not diffraction optics. It's diffraction optics is a diffraction element that's large compared to our feature size. Yes.
Okay. Okay. So are there any other questions?
We need to start the next session.
Yeah. Sure. So if not, then let's give the speaker another round of applause.
Thank you very much.